Hi, I'm Geoff Clarkson. In May of 2023, I was asked to lead a project team to develop a new part on assessment of fiber reinforced polymer, or FRP, equipment for API 579. In April of 2024, I provided a live online seminar to members of the API 579 Fitness for Service Code Committee to provide education on FRP. The session covered material on design using FRP, damage mechanisms experienced by in-service equipment, detection of damage, and overview of repairs, monitoring, and the contents planned in a part in API 579 to assess the fitness for service of FRP. The live session is being recorded here to be available as an ongoing resource for API 579 committee members. Since the initial session, some questions have been raised that have provided opportunity to add some additional explanation, so new slides or new material has been added to this from the original presentation. This video is the third of 4 videos. The agenda for the videos is shown on this slide. Video 1 discusses the introduction to FRP, particularly with respect to design. Video 2 discusses FRP damage mechanisms. Video 3, this video, describes non-destructive evaluation to detect FRP damage. Video 4 describes remediation, mitigation, and monitoring, and as well provides an overview of the FRP part for API 579-1 and Fitness for Service 1. The key items for non-destructive evaluation of FRP are that several non-destructive evaluation methods are available to detect FRP damage. 2, inspector certification is available for all methods that are going to be described. 3, some methods do not require calibration standards. And 4, conventional UT can be used for screening in some cases. There's a bit of a history to non-destructive evaluation detection of FRP damage. In the 1960s, NASA found that damage to FRP is indicated by attenuation or energy loss, or the propagation efficiency of stress waves generated, such as from ultrasound or applied stresses. In the 1970s, acoustic emission testing was developed to qualify new FRP vessels, and it actually works off of one of the principles that NASA identified, which is the propagation efficiency of stress waves. Later, some parallel relationship has been developed showing ultrasonic pulse velocity decreases with increased damage, and that becomes a tool that can be used as well. Adopting non-destructive evaluation started with acoustic emission testing, which was adopted by ASME for construction code use, and it's included in ASNT certifications. For example, you can find references to that and documentation for that in Boiler and Pressure Vessel Code sections 5 and section 10, as well as in ASTM E1067 and ASME RTP1. Ultrasonic methods are used to identify possible overt flaws using conventional training. This is particularly applied in the aerospace, for aerospace applications. And attenuation methods are not yet adopted by ASME, or are they included in ASNT certification. The methods and the techniques involved in acquiring data are not adopted. It is included in ASTM E1495 and ASTM C1332. Inspector certification is actually a result of training, experience, and examinations. It's required to create proficiency, competence, and accuracy of data acquisition. The typical certifying bodies are API, of course, ASNT, and the National Board of Boiler Inspectors. Certification must be relevant to the inspection method and the techniques to be used. A bit of a comparison of damage detection using non-destructive evaluation. For steel, we use NDE to detect overt flaws, defects, and discontinuities. And this is where the basis for a lot of non-destructive evaluation thinking comes. With FRP, well, we can identify cracks that are open to the surface, and the non-destructive method for that, of course, is visual testing. We can also detect properties of the polymer that then can provide the current condition. In other words, we can detect the things that will give us RFM, as we talked about in video 2. We can also detect the boundaries at damaged polymer, or between damaged and less damaged polymer. For structural damage detection in FRP, there are really 3 methods that we can use. There's acoustic emission testing, and it was actually developed with the primary purpose of finding structural damage. Acousto-ultrasonics, this is at the core of a methodology developed by NASA, and then attenuation-based ultrasonics, which actually adapts what NASA did, and in fact, with attenuation-based ultrasonics, we're typically able to use conventional ultrasonic equipment. There are 2 methods in particular that require calibration or reference specimens. These are things that will actually give us a reference point to a known measurement or a known destructive value. The reference sample has to be the same as the material that is being tested and should be as new, or basically from the new equipment. Acousto-ultrasonics would follow the process given in ASTM E1495. The inspector can be certified under ASNT, SNT, TC1A. They actually recommend that you use ultrasonic testing before AU testing to find areas to avoid. This is kind of an interesting thing because there are no specifications for how to identify what to avoid. And data collected in the field can be used to quantify the extent of damage that has occurred. Attenuation-based ultrasound, or UAX, can be used basically following ASTM C1332. Inspector can be certified under ASNT, SNT, TC1A. Some modifications to C1332 are required for use with FRP. The interesting thing is that the process will work, and it's been shown to work. However, C1332 states you shouldn't use this on FRP because because the attenuation levels are quite high. There are ways to work with that. Data collected in the field can actually be used to quantify damage to the FRP, and we actually need to use aged and unaged calibration samples for setting up attenuation-based ultrasound. By the way, we should be using aged and unaged for AU, or acousto-ultrasonics. But there are ways, there's a very conservative method that could be used with acousto-ultrasonics if you only have an unaged sample. Methods that do not require calibration specimens. And remember, a calibration specimen may not be available from FRP, partly because what you're inspecting or what you're assessing is 20 years old, and nobody kept a cutout from when it was new. So we have no way to get a new calibration specimen from it. And we don't want to cut a hole in it in order to remove a cutout so that you can get one. One method is actually a method known as ultra-analytics, and it's a patented attenuation-based ultrasound method. The inspector can be certified using SNT TC1A. Data collected in the field can be used to quantify damage, provide RFM values. And acoustic emission also does not require a calibration specimen. The criteria were developed for new equipment. It provides a conservative go or no-go result. In other words, it's either fit for service or not fit for service, but it does not provide any measurement of the damage that can be used in further assessment. It often requires analysis of field data. We actually have a part in draft at this when I record this, and NXE provides a step-by-step process for attenuation-based ultrasonic inspection. So with that, we use a transducer with a delay line. For each test location, record a reading to determine the available pulse voltage applied. We call that F sub 0. This is not in contact with the test material, so we'll come up with some value from an A scan of the reading that comes back from the face of the delay line. We then couple the delay line to the contact surface, and what we find is the reflection from the contact surface, which is F. This should be occurring at the same time as F sub 0 on the previous slide. Now you'll notice that we actually have a full A scan probably showing a reflection here from the back surface. And in fact, what we'll do is we could even potentially use the same reading or a different reading, use the different reading at the same location, coupled contact reading, determine the reflection from the back surface, that's B1, remember this was F here, and the transit time. Now this transit time can actually provide a thickness estimate and just for some velocity determination. But the transit time definitely is related directly to the thickness. For each reading that you get with an identified back surface echo, determine the net attenuation coefficient according to this formula. Straightforward, fairly simple. It does require post-processing because there is no equipment available on the market that will provide this number to you today or provide this number to an inspector today. So the inspector is going to have to do some additional work. There's still a relevant use for conventional UT, and that's for estimating crack depth. For those of us who've seen the video or paid attention to the damage mechanisms, this will be familiar. We have a crack forming in a process side surface, and you can see how this crack is translating. This is what happens when cracks form in FRP. The more damaged polymer cracks first. It's usually on the process side or exposed surfaces. And so there may be undamaged material behind it. And in fact, at the interface or the transition from the damaged to the undamaged, we'll see that the damaged forces the cracks literally to turn and follow the interface with the damaged material. This will show up as an intermediate reflection that could be interpreted by conventional inspectors as a flaw or a defect. But this will give us, the time difference here will give us the depth of the crack. What actually happens is that this reflection is normally caused by a change in the sonic velocity from this undamaged material to the damaged material, and that the interface where that change occurs is what creates the reflection, because all reflection and ultrasound are created by a change in acoustical impedance. We can then estimate the depth. If we don't have any cracks, we can still generate a reflection at the interface of damaged and undamaged FRP. And that's because the reflection isn't so much created as a consequence of the crack dislocation, but it's created by the velocity change from this relatively undamaged material to this damaged material. And so you can see we get a reflection. We actually get two reflections here that resolve into two slightly different reflections because they're so close together. The time, the delta time, or the difference in time from one to the other, is due to a change, of course, is due to a change in sonic velocity. For example, look, the space between here and here proportionally is not the same here, and that's because the sonic velocity is slower here. What happens then if we assume a constant sonic velocity, this will tend, using this transit time, will tend to overestimate the damage depth. Also works well. Damage can actually increase the detected thickness of FRP. If you have a new thickness and a sonic velocity reference for new FRP, you may actually see the sonic velocity go down, or if you use the same sonic velocity, the thickness will increase. When it comes to determining thickness, we could actually use a conventional calibration sample like we do with steel or metal alloys. Drawings may actually provide some useful information on thickness, and recognize that thickness variations are allowed within most construction standards. Ultrasonic testing is reliable, however, for determining thickness when a clear backwall reflection is present. If we cannot get a clear backwall reflection, then there's other considerations to have, and we'll talk about those later in this presentation. Based on data, what we're actually seeing here is that we have essentially a normal distribution of sonic velocity with a mean sitting somewhere around 3 millimeters per microsecond, which is 3,000 meters per second. The lower confidence limit, in other words, where we believe that say we've got a 90% confidence limit here, the lower confidence limit is about 2.87 millimeters per microsecond. You could use that value as a pretty reliable number. If data can't be resolved, for example, if we can't get a usable back surface reflection from an A scan, I would classify the component as not fit for service or inconclusive. And generally, if we're dealing with fitness for service, something that is inconclusive is in a no man's land, isn't it? When we process inspection data, or continuing to process inspection data for acoustic emission testing, there are specific instructions provided in Section 5 and as well in ASTM E1067. The instructions will provide fit for service or not fit for service result. In the event of a not fit for service finding, the standard actually recommends UT, but again, methods are not provided, nor are any criteria or specifications. So it's kind of a gray area there. Acoustical ultrasonic data is processed a little bit differently. The data output is a value called stress wave factor. And essentially, stress wave factor is proportional to the inverse of attenuation, which means that if the attenuation value is high or large, the stress wave factor will be low. And in order to use this, ideally, we need 2 reference calibration samples. Those are required to give some relationship of the stress wave factor and RFM of the equipment. So, for example, I'm giving this chart here, and I'm calling it an AU proportionality curve, where I've got 2 reference specimens. One with an RFM of 100%, so it's from new equipment, and we've got a stress wave factor of just over 0.6. The second one, we have 80% RFM value, so it's been in service for some period of time, and we have a stress wave factor somewhere around 0.35 or something. Essentially, we look at a pretty much linear relationship between RFM and stress wave factor. So if we connect those, we come up with this curve. There is a bit of a challenge. This curve intercepts the 0 line, and the stress wave factor is a real number. It has to be greater than 0. It intersects the 0 line at, say, 59%. That doesn't make sense. The this intercept should be less than 40%, or we're going to require additional reference samples. So this wouldn't be quite. This would probably be not conservative for use. Okay, and in fact, I actually provided a workshop with this, where the specimens that I had provided were used, and but one of them was not aged for a particularly long time. If we only use 1 reference specimen, we get very conservative results. You can see here that I've got, if I take that original new specimen with say, a stress wave factor of 0.65, RFM of 100%, and I say, I know that at a stress wave factor of 0, I should have an RFM of 0. It makes sense. If we project it straight down along this curve, then what we will get is some value, some very conservative value. And for example, remember from the previous slide, this is what the curve looked like on the previous slide. You can see this one is much more conservative to provide this. For attenuation-based ultrasound, the data output from the component tested will be, they'll be the attenuation coefficients from the equation that I showed earlier. All A scans and thickness with damage, and all of the A scans and the thicknesses with the damage depth estimates will also be provided. We actually need data for 2 calibration samples, just similar to what we just discussed for acoustical ultrasonics. We need a sample from the new component. What we need is the average attenuation coefficient, the RFM, and the transit time. And then aged from the new component. In other words, it could be a cutout after a period of time. In video 2, we actually provided an example where a cutout had been removed from some equipment in the example calculation, and we had that second cutout available for testing. Then what we need from this is the average attenuation coefficient and the RFM. What we'll get is a chart, a proportionality chart that looks similar to this, and we plot the log of RFM versus the attenuation coefficient. And in fact, this curve will be a linear curve with the formula similar to some slope times the attenuation coefficient plus a constant. And the reference specimens will provide these two values so that we know that, for example, the RFM is 100% here because the log is 0. So we actually get a curve similar to this. There is no way to make a conservative curve with for UAX proportionality if you only have one specimen. The reason is that we don't know where this endpoint goes at all. With stress wave factor, we do know where the endpoint can go. I'm going to talk a little bit about the advancement that's available, and there's some patents involved in this, so we're only saying that this is an option, but the other methods are perfectly usable. We call this UAX plus for this discussion. The data output actually directly is RFM values for all readings as well. You can get A scans and thickness with damage depth estimates as well directly from this. An overview of non-destructive evaluation is that actually acousto-ultrasonics, this is a typo, I'm so sorry, it's AU and UAX methods can quantify the damage to FRP. Quantitative values can be used in fitness for service assessment. Acoustic emission testing can provide conservative go, no-go results with no data that can be used in engineering assessment. So if you get a go value from acoustic emission, then, or a fit for service value, then you're fine, continue moving. There's no reason to really question that. If you get a not fit for service result, there's no further action you can take on that except to perhaps use another method in order to try to quantify the extent of the data and reevaluate at a level 2. Ultrasonic testing can provide information on thickness, the depth of damage that exists, and as well the depth of cracks. Inspectors should all be certified as an SNT TC1A, and data from non-destructive evaluation can be used in FRP, in the FRP part for API 579-1 and ASME FFS-1. Continuing with exactly the same example of the sump level of a scrubber. In the last presentation, we had a cutout available that we examined and performed destructive testing on using ASTM D790 and 3-point bending to determine the RFM was 57% of new. This is after 16 years. We actually used UAX plus for these results. After 16 years, we have the RFM at 56% using non-destructive values. 21 years, it resolved to 53%, and 23 years, it resolved to 50%. No results are available at this time for UAX using ASTM C1332, and no results are available for this equipment using acoustic emission testing or acousto-ultrasonics. But you could get similar results for acousto-ultrasonics and probably similar results for attenuation-based ultrasound. No testing has ever been done on this equipment using acoustic emission. That's the end of video 3. I invite any questions from you folks, and by all means send them to me or contact me at these coordinates. I'll be very happy to answer, and perhaps if the questions are inspiring enough, we'll update this video. Thank you.